help us, and why now it's becoming more and more relevant. After we have discussed about these questions, these points, I'm going to present two main fundamentals, I believe, efforts and outcomes of the work we have done in our laboratory. First one has to do with the end-to-end infrastructure that you need to have in order to support and really use this kind of new technologies. So the fundamental infrastructure, let's say, and then the digital twin architectures, the specific designs, the specific conceptual frameworks that exist and we are using in order to develop a specific digital twin architecture in the context of the MetaCities project, particularly since we are in the specific Spring School. And then I'm going to present four different, seemingly different pilots or scenarios where our research teams have used these technologies in order to provide real-life pilots and useful services. So let's start with why why processing is more and more done on the edge and the far edge. And the first point I would like to make is that it's not a question about edge versus the cloud. This is a myth that the edge is fighting the cloud. They are not fighting each other, they are complementing each other. Why? Because the edge is especially important for local autonomy, privacy, and safety. Devices may need to make decisions immediately without depending on the remote infrastructure, on whether there is connectivity with the backend or the quality of the connectivity with the backend. At the same time, the cloud it still is extremely important and has a critical role. But now we see more and more that it is better suited for, let's say, large-scale model training, long-term storage, global optimization, analytics among many sites and devices. So it's not about whether the edge is better than the cloud, but how we can better distribute and use the intelligence across the range between the edge and the cloud. And why is that? A simple answer to this question is that we have entered a new era of applications. In more, let's say, before 5 or 6 years, there was a tendency, a notion that, okay, now we have the cloud infrastructure, so let's put everything on the cloud. Why? Because technically the cloud can give you infinite resources. We can have as much bandwidth as we want. We can have as much processing power as we want, CPU, GPUs, we can have storage, we can have everything. So there was a notion of putting everything on the cloud. However, this didn't solve everything, particularly when the applications require low latency. For example, emergency situations, as we saw at the previous presentation, mobility, healthcare, industrial scenarios. In such cases, even the smallest delay can matter. So in these cases, the cloud is not the best way to go. For example, and since we are in the MetaCities Spring School, let's see a typical example indicated with the red letters. If we assume that we have a car that is driving with 120 kilometers per hour, this vehicle will run 23 meters in 500 milliseconds, and that is ideal. We can easily understand that this can make a great difference when you are considering braking, speeding, steering, or when you want vehicle networks and you want your vehicle to accurately understand its surrounding. 23 meters is a long distance and can make a great difference between an accident or not. And still, this is not the end of the story, because this has to do with what we call functional requirements. How fast the communication is done, how fast the processing is done, and so on. But in modern applications, we need to take into consideration a lot of non-functional requirements as well. For example, as I said before, we can say, and technically we are correct, that the cloud can give us abundant resources regarding bandwidth, processing power, capacity, and so on. But they are not for free. They are quite costly. And depending on what you want to do, this cost can be very, very high. So this is another disadvantage of putting everything on the cloud. Then we have security and privacy. I know that you had a very nice cybersecurity related presentation at the morning, at the first session. Make no mistake, whenever you are transmitting data over a public network, no matter the security measures, your data is at risk. And with applications handling, managing more and more sensitive private data, these kind of requirements, non-functional requirements, are also very important. And this is also another area where the edge can help a lot. And then we go to power consumption. All the operation that happens on the cloud needs power. And at this point, we can see a lot of studies indicating that cloud computing is nowadays one of the most energy hungry and energy demanding technological domain that exists. Both the power you need to run the data centers, as well as the power you need, for example, to cool your data centers, is a major, and it is becoming a major problem for current and particularly future applications. And of course, data will only keep on increasing. We saw in the previous presentation, we are going towards 6G networks. We are going towards massive connectivity. We are talking about trillions of devices continuously creating data. So in the foreseeable future, the volumes of data are going to be just increasing and increasing exponentially. So we have what we call data obesity. We cannot handle data, this kind of data, solely only relying on the cloud. We need to think smarter. We need to think more intelligently, and we need to exploit and harness the power of the edge cloud continuum. This is one question. The other is AI. Why AI and why now? The simplest answer to the first question is that AI nowadays indeed can help us solve problems that we could not solve previously. Some of them may be easy to solve and straightforward, but many real-world problems are too complex, like perception, anomaly detection, localization, prediction, decision support. All these kind of problems AI can help us. I don't know if it can solve them everything, but certainly can help us. But why now? Why have we seen the last 5 years this explosion of AI utilization? This is a very nice figure I have found, and I am using it in my presentation for the last 1.5 to 2 years, because it clearly indicates the reason why we have entered in this final era of AI big data. As we can see, around 2020, we shifted eras. We shifted we move from mobile plus social media eras where the devices that could do processing could be measured in billions, and we moved towards AI big data, where the devices that have substantial processing power to really help us with processing and with AI can now be accounted into trillions of units. So there is a lot of much more processing power on the edge that we can and we must exploit and we can harness. And also, let's not forget the business aspects. We see here a prediction. This, as I said, this graph is 2 years old, I think, where it indicates that AI-related growth will boost global GDP by $16 trillion by 2030. 2030 is in 3.5 years, so it's very close, right? So we are in the middle of this era, and we have a huge market in front of us that it is very, very important to use and use efficiently. The other thing that has happened during the last years is to clear that another myth has cleared. So in the past, it was popular to say that, okay, AI is done only on the cloud. It's only for the cloud because you need data centers, you need processing power, you need a lot of CPUs, a lot of GPUs, a lot of storage, a lot of memory, and so on. This is not true. During the last 2 or 3 years, we have seen a dramatic shift of AI towards the edge. Why? Because now we have the capabilities. We have the edge capabilities to run and run efficiently AI trained models. We see specific examples of efficient AI operation on the edge regarding, as I'm indicating, perception from vision, audio, radar, sensor fusion, and so on. So now AI is not only for the cloud. This is the takeaway from this slide. We can have AI on the edge. Of course, the cloud still remains, as we said, a very important aspect, but we are now using it for, let's say, heavier and more global tasks, if you want, as I'm indicating here, like model training. Of course, model training still happens on the cloud, but the trained model, the trained machine learning model can very efficiently be executed, be run on the edge. Fleet level learning, global planning, monitoring, and data governance is some of the aspects that still cloud has the first part. And now we move on to the digital twin. We saw AI. I hope I have clarified some things, and we see why AI and edge cloud continue can work very well together. And now we have digital twin. Digital twin, as I said previously, is another very, very popular buzzword we are continuously hearing about. But what is digital twin? If we wanted to give a formal definition, let's say. So a digital twin is a living virtual model of a real product or an asset or a process or a complete organization. The idea is that this model is continuously updated with data from the real world, so it can, in real time, be represented of the current state of the physical system, or even the transient stage of the physical system. But still, this is not the end of the story, because up to this point, what we have is a very good IoT dashboard. The important thing is the interplay that the digital twins allows us to have between the physical world and the virtual world. The important point is that the digital twins must allow the researchers, the developers, to test decisions before applying them in the real world, to test what if scenarios in the virtual world in such accuracy that they can interplay with the result that will have this kind of what-if scenarios to the real world. So instead of experimenting directly on the infrastructure, we can simulate scenarios safely. What are the benefits of this? First of all, reduce the risks. Test failures, bottlenecks, trade-offs, we can evaluate them in a very safe environment. Cut costs. Don't forget, as I said, the non-functional requirements. All these simulations have to do with very expensive or dangerous situations. So by doing them in a simulation environment, we can drastically reduce the cost and the danger that these scenarios entail. And I'm going to show some examples that we have done in our pilots on that aspect. And through this process, we can certainly accelerate innovation. And why now? So we understand how we hope digital twins are going to help us, but why now? The first reason is the growth of IoT sensors, the growth, the advancements in embedded systems. We now have a wide range of sensors and actuators, low cost, low power, very small, that we can use and really understand and interact real time with the physical world. So we have now access to real-time data directly from devices, buildings, vehicles, and environments. The second reason is exactly as we said, the scalable cloud and edge computing. This makes it possible to process large amount of data, large volumes of data, and run simulations or analytics closer to where they are needed, closer to the actual problem. And thirdly, AI and generative AI. These are new technologies that make models easier to build, interpret, query, and improve. Finally, let's not forget the business aspects. Business and societal environments are highly volatile. They are changing continuously and in many cases unpredictably. So cities, industries, and organizations need scenario planning because conditions can change quickly and we need to be aware of it. Digital twins, in that sense, becomes an important tool because it allows us to have the data, computing power, AI methods, and operations to build accurate digital twin models and better understand the physical system. This is the goal. But in order, and now I move to the two infrastructures that we have designed and developed in our laboratory. In order to really harness this kind of potentials that cloud, edge, cloud continuum gives us, AI, digital twins, and so on, first of all, you need to have the fundamentals. And the fundamentals is a very well-structured end-to-end infrastructure, able to be expandable and extendable in order to integrate these kind of technologies. So in our laboratory, we have developed such an infrastructure covering all aspects from the sensor up to the backend. So in the left-hand side, we have the edge layer with sensors, gateway, and so on, where what we can do, apart from acquiring data, is run AI models, run the algorithms closer to the source in order to satisfy the processing and timing constraints. Furthermore, what this new approach allows us to do is what we are calling here at the edge processing, lightweight digital twin synchronization. The goal here is to send state updates and not raw data, because raw data is just increasing volumes of data. But if you send only the state, then you have much less data to send, and more accurate representation of the physical world. Then also we have the gateway, for which I'm going to have a dedicated slide. And then we go to the cloud layer. Here we have the physical models, as we see here. The physical models of the digital twin domain, which are model definition of the real world assets. These can be devices, these can be systems, or this can be operations, as I'm going to show in the following example. Furthermore, we can model the behavior of the system. That is, how the asset is expected to behave when the situation changes. To support these capabilities, we need to have digital twin functionalities, a specific component where we have the AI analytical models, support for prediction, detection, etc. So as you see here, in order to have a complete cloud infrastructure, you need to have communication components like HTTP API gateways and MQTT clusters. You need to have databases, and you need to have clustered databases, both SQL and non-SQL databases, and a lot of other components that need to work together in order to give you the required level of functionality to support digital twin and AI. At the next slide, I'm making specific reference for the gateway. I believe that the gateway in the modern CPS is one of the cornerstone points in order to really exploit AI and digital twin. Why? In the old days, the gateway was considered by many as just an aggregation point and forwarder point, just a router. This has changed quite a lot. Now the gateway is a processing element with a lot of duties that need to be supported. Why? First of all, as we said, we now have advanced sensors and actuators. These are specific low-cost devices that allows us to understand the physical world, but also to interact with the physical world. And the IoT gateway nowadays is considered as the middleware between the edge and the cloud. So here we have the aggregation point, we have multiple wireless interfaces that the gateway needs to support because there are so many choices and options regarding the wireless communications. So we must support the Bluetooth low energy, Wi-Fi, 5G or 6G technologies, as we saw in the previous presentation, LoRaWAN. All these wireless interfaces are inherently heterogeneous. So the gateway needs to somehow harmonize data. Or additionally, the gateway needs to deal with data management issues, device management, security, as well application integration. All these are new components, are relatively new components, and they have quite demanding processing requirements. That's why now we see gateways implemented in the forms of Raspberry Pi or clusters of Raspberry Pi, as we have done in this particular case for a pilot of a European project. And a few words about the cloud infrastructure. Now here we know that most of us know that the current cloud infrastructure is built on microservices, which support independent service deployment and help us with the scalability of the system, as well with better handling of faults. Because in this case, when we have service faults, these are not affecting the entire system, but some specific parts, thus allowing the remaining parts of the system to be accessible. However, this approach, the microservice architecture, comes with an unavoidable overhead in operational and orchestration complexity. That's why we need at least two tools to be familiar with. First of all, we have the Kubernetes as an orchestration platform, which allows us to automate deployment and management, scaling, load balancing, and so on. And furthermore, Docker as a container virtualization, which allows us to have lightweight containerized environments and dependency isolation and portability. And now we move on to the second development of our research group, which has to do with the digital twin, particularly digital twin in a smart city, which we don't consider it just a 3D model of the city, but it combines multiple layers of information which are separated in a specific layered approach, as we see here, which, following a bottom-up approach, contains, first of all, we have the terrain, then we have the buildings, the infrastructure, the mobility services, and the IoT services. This layer built on top of each other to create a different digital representation or a different abstraction of the city. Data from the physical city feeds the virtual model, and the virtual model can then be used for simulation and decision making. For example, following this approach, we can simulate traffic changes, emergency responses, energy demands, infrastructure failures, and so on. Furthermore, it is very important to highlight the idea of the feedback loop. The physical city provides data to the digital twin. The digital twin produces insights, and then these insights guide actions back to the physical city. So we have this, let's say, closed control loop between the physical world and the virtual world. But to do that, we need to use specific conceptual frameworks. One of the most widely used or popular frameworks for digital twin architecture is what is called 4+5 framework. 4 refers to, let me see if I have, okay, perfect, refers to the internal elements needed to build a digital twin city. These include, first of all, the infrastructure, which is something that we are very focused on, which has to do with the physical and the digital systems that support the city. But this is not enough. We need to focus also on the data resources, which include information collected from sensors, services, urban systems, so more abstract information. Also, we need to focus on platform capacity, which refers on the capacity regarding software, computing, processing capabilities, analytics capabilities, and so on. And finally, of course, the application scenarios. What are the specific real use cases a digital twin will focus on? It may be mobility, it may be planning, it may be energy, it may be healthcare, safety, environmental monitoring. A wide range of scenarios can be included in this internal element. And finally, we have the 5 refers to the external elements, which are critical supporting elements, non-technical elements. So we are talking about strategy and mechanisms, stakeholders, funding, business models, standards and evaluation approaches that we need to follow and we need to agree on. And of course, cybersecurity. This is very, very important in order to highlight that digital twin city is not only a technical system. It needs collaboration between technical persons, governance, investments, policymakers, and many other actors. Following this approach, in the METACITIES project, we have ended up in this architecture, the main message of which is that we require an integrated architecture where physical urban systems, IoT data, edge cloud infrastructure, digital twin models, AI services, and user interfaces work together. Also, following a bottom-up approach. At the bottom, we have the physical city assets and the sensing devices. Then data is collected and processed through the edge or the cloud infrastructure. And on the top of that, digital twin models represent the city and enable simulation, prediction, and optimization. Finally, applications provide services to the actual end users, planners, and operators, as well as decision makers. For example, in the context of metacities, these can be ministries, can be municipalities that they are going to use this kind of architecture, not technical persons. Okay, this is the main idea, that such architecture must be usable not only from engineers, but also other actors. And I can say mainly other actors. And now we are going to move a little bit faster to the specific examples that we are using this kind of technology in our laboratory. First of all, localization systems. Localization is an integral service of a wide range of applications. So we have developed this system where we are using Bluetooth low energy devices and receive signal strength indications in order to estimate the distance between different sensors. We do edge computing in order to filter this data because these are very noisy data, and we are using AI models to compensate for the noise radio signals in order to classify these models. What we are able to do with these three main components is provide indoor localization at GPS level, a technology that it is agnostic to specific communication protocols or vendors, since RSSI is by default emitted by all wireless interfaces. And we are using efficiently AI and filtering in order to make these kind of signals much more usable. This is the workflow of our system. The main parts where the processing happens is the RSSI processing and filtering, since RSSI is a very volatile system and very hard to manage, and machine learning distance estimation. These two components can be executed either on the edge or the cloud, depending on the scenario and the speed, the low latency requirements we need to satisfy. So what we are doing is we are transforming such bad or difficult to manage signals to much smoother signals, and also we can classify a connection as line of sight or non-line of sight, so either there is an obstacle or not between the communication nodes in a very accurate way. If we combine, so what is the end result? Okay, we did that, and so what is the benefit for the end user? If you use this kind of technologies, what we have achieved is to reduce the error or the accuracy from 1.67 meter just to just 15 centimeters. If you imagine indoor scenarios with an accuracy of 15 centimeters, you can easily locate a phone, keys, eyewear, and a lot of other equipment in a typical household. Furthermore, what we have achieved, and we see that in this graph, is the following. In this x-axis, we have the number of the devices that have line of sight with the target. What we see with the green columns is that our solution not only is much more accurate, but it is independent to the number of the stations with which the target has line of sight. So we have a much more efficient solution that can be deployed in much more harsh environments. compared to the performance we had without using the combination between machine learning and edge computing. And these are used also for healthcare systems. We are using a lot of different sensors, as we have mentioned, in order to do what? To promote inclusive technologies. We combine technologies, so we combine localization technologies in order to do what? In order to understand the mobility patterns of a person in a house. A person that can be an elderly person or a person with impairments. Through this processing, what we get is the ability to detect everyday life activities of a specific person. These include cooking, resting, sleeping. So we have the pattern. We can detect the pattern, the personalized everyday pattern of a specific person. And through continuous monitoring, we can detect deviations from this pattern, or we can also combine fault detection with the mobility pattern in order to identify what we show here, which are problematic areas of a specific real-life household. These are the areas where the most incidents of fault detection have been identified. And then we can provide stimuli to the end users in order to avoid this kind of situations. I'm going to skip this slide. And in order to show also two examples where XR and VR technologies can also be used. In this case, we have Emerge XR, and this is quite closely related with what you saw in the previous presentation. Here, we have the responder that comes with AR-enabled devices, and what he or she sees is this kind of user interface. So by analyzing and by continuously analyzing the body posture, movement, medical context, using AI-driven pose estimation and sensor fusion, we can detect and we can provide guidance for specific emergency situations like blood circulation assessment, CPR positioning, and neurological evaluation. So in this way, we can provide guidance to the responder of what he or she must do. But what it is very important here is that everything must be done very fast with as much low delay as possible. That's why we also use 5G private networks that we have in our laboratories, or we are using from our colleagues in the research project, which at the end of the day, we saw that we can provide edge support almost instantly to the responder and react in real time without interruptions. Just to give you a hint, so we have an end-to-end pose latency of less than 40 milliseconds. This is end-to-end. This is not only the network. Frame upload latency between 10 and 40 milliseconds. A pose update rate of 10 Hz, so we can support 10 different poses in 1 second, in order to provide this kind of guidance. Furthermore, what it is important is to emphasize on the telemetry and the monitoring of the Emerge XR. Using technologies like OpenTelemetry, Prometheus, and Grafana, we can collect real-time metrics from every component, including network metrics like throughput latency, rendering performance, AI inference timing, and many more. Through this monitoring approach, the Emerge XR, what has demonstrated is that XR services supported by cloud technologies can be deployed and validated on next-generation communication networks. We have done a similar, let's say, use of XR technologies, but now for training. So here we use XR and digital twin. Why? in order to provide immersive VR training for high-risk industrial environments and particularly or specifically port operations. Here we collaborated with the Port of Thessaloniki, and the key idea is that in many cases they have dangerous or expensive scenarios that cannot be practiced in the real world. So what we have done is we have created digital twins of what? Of the infrastructure, of the equipment, and the hazardous operations that the trainee must practice on, must be trained realistically without operational risks. And we have developed 4 validated scenarios upon which more than 100 participants have been trained, around 150, I think, and we have achieved excellent usability score and a TRL level of 7. In this case as well, every interaction is measurable through telemetry. So this gives us the instructors objective insight of the trainee performance and the procedural compliance. What I would like to highlight here is that Portal XR is not just a VR application. On one hand, it is based on the Atlas Cloud infrastructure I previously presented, and on the other hand, we exploit real-life digital twin models which provide realistic representation of port assets and operations. And on top of that, we are providing a Unity-based XR simulation to do the training. Finally, and in order to emphasize on the need for non-technical perspective, we have used and we have integrated formal and well-established educational methodologies into the training program, which allows us to have authoring and personalization tools which can create and dynamically adapt the scenario depending on the learner performance. Finally, just give me a couple of minutes, I'm a little bit off, but I would like to emphasize the connection of this kind of technology with 6G networks. All these are important future research domains that correlate between the coming 6G networks and technologies that exploit edge, cloud continuum, digital twin, and AI. We are particularly focusing on ISAC, integrated sensing and communication, RIS, reconfigurable intelligence services, and terahertz access service region. Why? Because there are a lot of challenges there to meet. There is a lot of room for research, dealing with severe propagation and locus losses, narrow beam alignment, mobility sensitivity, hardware impairments, and so on. And in a project called 6G Therapy, we are directing our research in hardware-aware PHY experimentation because their edge devices collect and process real-time sensing and communication data. AI optimization and dataset strategy. Here we are going to use the cloud infrastructure to support deep reinforcement learning, training, orchestration, and large-scale simulation, as well as the interplay between simulated and real-life experiments. So digital twin will also come into play in this aspect. Cross-layer co-design. Here the edge cloud continuum is critical to enable coordinated optimization across different layers, physical, MAC, sensing, network, in order to have scalable 6G deployments. And finally, measurement informed calibration. Here we are going to focus on distributed measurements and cloud-assisted calibration in order to improve alignment or correlation, if you want, between the experiments and the simulations. All these directions greatly exploit these technologies that we think will make the difference in the future. So concluding, I think future cyber-physical systems clearly require intelligent edge cloud continuum where processing, AI, decision-making, and distributed operation will meet very strict demands regarding latency, privacy, scalability, and reliability. Digital twins are changing. They are actually evolving from static visualization, nice to have tools, into cornerstone real-time operational platforms that combine sensing, simulation, AI, analytics, and so on to support smarter cities and cities of the future as the driving force, as well as healthcare, industrial training, and many other application domains. AI architectures and telemetry-driven systems are also very important to implement services like localization, industrial training, 6G, Isaac ecosystem, and so on. And finally, it is a strong belief that the convergence of classical embedded systems, IoT, cyberphysical systems, AI, cloud infrastructure, digital twins, and 6G technologies will create a unified technological ecosystem for future resilient, scalable, and don't forget, human-centric applications. So that's it from me. I'm a little bit late, but thank you for bearing with me.